One second. All right, we're recording now. So welcome everybody. And Paula, thank you for taking over.
Thank you, Dirk. So welcome also from my side. I'm happy to see you all back here in this Laws of Nature series, and I'm very happy to announce our first speaker of this winter series, Professor Peter Pickl from University of Tübingen. So he was formerly a professor at Munich, where he unfortunately left, but now he's in Tübingen, and I think he's happy there too. He's teaching mathematics. He's a professor in the working group of mathematical physics, and today he will tell us about his main area of research, namely effective equations, bridging the gap from the microscopic to the macroscopic. So Peter, please go ahead.
So thank you very much for the invitation. It's a great pleasure and honor to speak in this series, and I'm really happy to be the first speaker of this semester. As Paula announced, I'm going to talk about effective equations, bridging the gap between microscopic and macroscopic understanding. And I would like to start with some kind of motivation, which is a little bit pragmatic, but later I will come to the more honest motivation for topics in this direction. So think of a system of n particles with interactions. And if you want to control such a system with numerics or analytically, that's often impossible. For quantum systems, for example, if the particle number is roughly 10 or more, then you have no chance to do the full dynamics with a computer. Well, think of a system in 3 dimensions. So you have 30 dimensions where you have to model a wave function on. If you have 1,000 grid points in each direction, that means 1,000 to the 30 grid points for the system. And I think you see that computers will not be able to handle this at the moment. And what physicists do is they use simplified effective descriptions, or descriptions which cover the main feature of such a system, so which reduce a system with so many degrees of freedom to a fewer number of degrees of freedom, those which might be the most relevant for your experiments. And this is what physicists often do. And what one of my main research topic is to prove the validity of such effective descriptions with mathematical rigor. Of course, in particular, when there is an influence of the interaction on the system, well, if the interaction is negligible, it's often not so very interesting to discuss these effective equations. Well, this can be done for many systems, for quantum systems, for classical systems. You could derive the Maxwell's equation coming from a QED model and many things. So there's a long list which I could give. And since the list is so long, I decided to focus on some classical systems for this talk and this presentation. And as I said, the most motivation which is also there to study this bridge between micro and macroscopic world is that there are cases where you have reversibility on the microscopic level, but irreversibility on the macroscopic level. And to explain that is something which I found particularly interesting. And there's a discussion going on now for many, many years how this can be done. Okay, I would like to start as an introduction with a comparably simple situation to make clear what all this is about. And I start with what I call case 1. There will be case 2 later, which is a microscopic system, which looks in the following way. So think of n interacting particles. You might have stars or charged particles in a plasma in mind, and they are subject to Newtonian dynamics. So this is described by some trajectory on phase space. Q and P are the positions and velocities of the particles. I will not distinguish between velocities and momenta in this talk. I assume all masses are equal to 1. And the Newtonian dynamics tells us that the time derivative of the position is equal to the velocity. And the time derivative of the velocity now is given by a force. And the force term will depend on the position of all the particles. And I assume to be in a very natural setting, which is that the force which is experienced by the jth particle is given by this kind of pair interaction force. So I have a v coupling n to the -1 times the sum of all interactions. Now, the physicists among you might now say, okay, n to the -1 is coupling. That looks a little bit unnatural. Why should the coupling constant change when I increase the number of particles? Well, often this can be explained for by rescaling the system. I will not enter into this topic, but there is arguments which guide you in this direction. And if you don't see these arguments, well, let's see that for the moment as some academic problem, which is useful to make the more physical stuff later. And what you get now for the macroscopic equation is a law of motion for the density of these particles. So you have a cloud of particles, let's call it a cloud of stars, a galaxy, and there is a law of motion for this galaxy, and this tells you how these particles move. Now here, for the first part of this talk, I would like to give a simple heuristic picture for the non-experts and how one can guess or write down this effective equation for these particles. So I want to find an evolution equation for the coarse-grained empirical density of the particles. And I assume that initially my galaxy was built in a way that all the stars are IID with a given density rho. So there's a one star at a certain position and momentum. So position here, all points are in phase space in R6, and there will be a third one. And if I do that, I will get a coarse-grained probability, empirical density, which is just the ratio of the number of particles in a given volume V divided by the volume. This is something very natural. So the coarse-grained probability density now is defined by n is the particle number divided by V times n, so the volume of the particles. So this n here is to normalize this density here. The total number of particles will be n. Now, what is now the force which a particle experiences? As I said, well, the microscopic model tells you that each particle now moves in the pair interaction force. And in the effective model, I do the following. I don't consider each position and velocity of each particle precisely. When I ask about the motion of one individual, one of these stars, I do use this coarse-grained density to calculate the force which acts on the particle in good approximation, and assume there is some particle, some star or whatever sitting in the position Q. What is the force F bar Q this particle experiences? Well, the exact formula is it's the sum over all the other particles, or all the, in this case, instead of summing over all particles, I sum over different boxes. So I split up my phase space into boxes. The J is the label for the different boxes. Take the number of particles in each box, multiply with this coupling constant of my force, and take the force which the particles in this box, each of them has with this particle sitting in position Q. This is what we get. Now, using that n divided by V times capital N is the density, you can replace that easily and say, well, this is the Vj times the empirical density, where Vj is the volume of each of these boxes. Well, we can assume for this setting here that the volume is always constant, and we get this kind of formula. Now, this is a sum over many little volumes, so in good approximation, you can replace it by some Riemann sum. And this Riemann sum now tells you that this here should be the integral, close to the integral of this empirical density with F. So this is the empirical density at TQP times the force at Q minus Qj integrated over P and over the Qj's, which is the volume element which I've written here as Vj before. And what I get is something like a spatial convolution of the empirical density with the force, and all this as a function of T and Q. So this was some easy heuristics, and we expect that this force term should describe the motion of all our stars in our galaxy. It is important here, and this is what I want to emphasize, I will come back to this later, that this is an empirical density. So for the talk, I distinguish between probability densities and empirical densities. I think this is very, very important, in particular for the second part of this presentation. Now, what did we get? Now, we have this empirical density of particles. The particles move, so the density will be time dependent. So now this is, here there should be an M maybe. This is the empirical density. The particles move, so also the probability density will be time dependent. And we have a conservation of the phase space volume. So for the probability density, we have that n divided by Vn is constant. And we arrive at some kind of continuity equation. So the density at t, q, and p should be constant, which means that the time derivative of this density is 0. And the total time derivative can be written as the partial time derivative times the derivative with respect to q, times the change in q, which is q dot, times the derivative with respect to p, times p dot. And now we take what we had before. We know that p dot should be close to f bar. This is the approximation we have, or the leading order effect we expect from our force term. And the force we had before was the empirical density in convolution with f. Now, the law of large numbers tells us that this empirical density should later be close to the probability density if we assume that the particles are more or less independent. Therefore, when you write down the Vlasov equation as an evolution equation describing the probability to find a particle in a certain position and a certain velocity, you arrive at a nonlinear equation where here it's just again the probability density. Now, since the law of large numbers should hold in this situation, at least heuristically, they match. But one should always remember that this here is the empirical density, because interacting with just the possibility or a probability that there might be a particle somewhere is kind of unphysical. So I think this is very important, and also for the reminder in the talk. Well, in particular in quantum systems, you get similar evolution equations, some nonlinear evolution equation, again, where you have an interaction, which is the convolution of the probability density with V. And I think this is a weird object, because if a particle sits there and another particle has different options where it might be, you're not interacting with the average. And if you have a system of only a few particles, such nonlinear equations will not describe the evolution of your system. Only in the case where there's many particles and the empirical density and the probability density match, because of a law of large numbers argument, it makes sense to get these kinds of nonlinear equations. Okay, now we've discussed one case, which I called case 1, and I would like to now draw your attention to two distinct cases, which I would like to discuss in the next step. So again, we think of a large number of particles subject to Newtonian motion with interaction. And again, we are interested in cases where the total interaction has an influence of the dynamics. So following each particle, the influence of the interaction is of order 1. And we have these two distinct cases. Well, the first one is the one we discussed. So this is the case where the single interaction strength, so the interaction of our particle with each individual, is very weak. We have the 1/n coupling. But the number of interaction partners is huge. We assume that our force term is of a fixed order, so the range of our interaction does not shrink as n goes to infinity. So if we increase the density, the interaction partners get larger and larger. So we have many interaction partners and a very weak interactions. This is the case we just discussed, where we get some kind of law of large numbers behavior and so on. Well, another case which is very different from that, and which I would like to talk about, is the case where the single interaction strength is of order 1. So whenever two particles collide, the interaction strength, with interaction strength, I mean the influence on the motion of the particles. So the impulse or the momentum change of the particles at interactions is of order 1. But you only have a few interactions. This is the other options. Both cases, while each interaction only changes the velocity mildly, but you have many interactions, or each interaction changes the velocity significantly and you have few interactions, both give you that effect that the interaction has an influence of the motion of the particles, well, first on their velocities and then indirectly, of course, on their positions. So both fulfill these assumptions which I have, or this situation where it's an interesting system. Now let's discuss these two different cases further. Well, in the first case, if you could now ask the question, does a law of large number hold for each individual particle? So if I follow the trajectory of each particle, is there some kind of large numbers argument which I can use to replace my interaction? In the first case, the answer is yes. In the second case, obviously no, because you don't have weak interaction with many particles. Still, the second case can, and this I will discuss later, can be dealt with by using law of large number arguments, but not along the single particle. Well, each individual will encounter a kick, right? And this kick will very much depend on the details of the collision. But if you look at a cloud of particles, a huge number, and to see how they collide, there might be averaging effects and so on, but this is not what I discuss at the moment. Well, the effective interaction will be some non-linear external interaction of leading order. In the second case, it will be dictated by collisions of the particles. And what is, I think, very interesting is that in the first case, you don't have a change in the entropy. The entropy stays constant. In the second case, the entropy is in general subject to change. Of course, also in the second case, you could look at some equilibrium situation and the entropy stays constant, but in general, there's a change in the entropy. Why is the entropy constant in the first situation? Well, the interaction could be replaced by some external field, right? And you know, if you have a cloud, many particles, a cloud in external field, so no interaction between the particles, and you let them evolve, that the entropy will not change as the time evolves. The limiting equation in the first case, it's the Vlasov equation, which I've written down. In the setting case, you get some Boltzmann equations. Of course, you can generalize this setting to some kind of Vlasov-like equations. I will discuss a Vlasov-like equation in the main part of this talk, and you can also talk about Boltzmann-like equations. Now, as I have talked about entropy, and although there's many people in the audience, or some people in the audience who are more experts on entropy than I am, I would like to say a few words for the students, which I think are very important when we discuss entropy. And this will be interesting for things I would like to talk about later. So I would like to say a few words on entropy first. And the notion of entropy was introduced by Clausius in the 1850s. And the word entropy comes from the Greek word entropia, which means something like transformation. So it has to do with change. And what Clausius did, he introduced a quantity, and the idea was to quantify the qualitative fact that there is irreversibility in thermodynamic processes. So he saw that some processes are not reversible, and he wanted to have a quantity which pays respect to that. And he found entropy on the macroscopic description, which really does the right thing. It's a quantity which can only grow, never decrease. And when later people like Boltzmann and Maxwell gave microscopic explanations of the laws of thermodynamics, of course, it was interesting to see how the entropy introduced by Clausius can be argued for on the microscopic level. So Boltzmann is one of my big heroes. I think he's incredibly ingenious what he did, and how smart answers he gave in that short time to all the discussions about the microscopic system. This is really impressive. And he gave this microscopic definition of entropy, and his definition is the following. You take the logarithm of the number of microstates related to the set of macro variables defining your macroscopic state you are in at the moment. And if you do that and do some very simple combinatorics, you get the following formula. I've written down the following formula a little bit in more detail. So let's assume we are in a probabilistic situation. Even if you say it's Newtonian dynamics, the initial condition could be random, right? So we have a sample space, capital omega, and the elements in our sample space are these little omegas, which I have here. So these guys, which I have written here, these are the samples. So your initial situation was at random, for example, think of that. and initially you randomly created your galaxy and they started to move. Well, this gives rise to an empirical density at x and v. That also depends on t, but I didn't want to put too many variables now into the system, so this, of course, will be time dependent. Now, this empirical density, if you look at the empirical density and ask, like, given omega, you get an empirical density for the cloud. The same empirical density is represented by a huge number of microstates, and you could count all these microstates and take the logarithm of that, and this gives you the entropy. Now, if you do a little bit combinatorics, you see that instead of counting the microstates, if you have a density, you could also take the integral rho, ln rho. So this is, as I said, simple math to show that this is in fact the logarithm of the number of microstates. And then there is some constant involved, namely the Boltzmann constant. So this was his ingenious finding, and you see that this entropy here also will depend on omega. So the omega will still be there. This is something which I think is quite important. I will discuss in a second. Now, what's the idea behind the Boltzmann entropy? How does the Boltzmann entropy give you the microscopic explanation of the Clausius entropy? And here I would like to draw a picture. Now, we assume for the moment, to make things a little bit simpler, that we have a measure, a probability measure, which is invariant under the time evolution. Well, the measure which is invariant under the time evolution, this you all know, will be the Lebesgue measure on phase space. But the Lebesgue measure on the full phase space is, of course, not normalizable. You can't turn it into a probability measure. But let's assume we are on a torus and we have some kind of bound also on the kinetic energy. Then you could normalize your measure and you get a normalized measure. Now, the space I'm drawing here is the space R6n. So this is the phase space for all my particles in the system. And I could do the following. I could look at the different macro variables and say, okay, let's think of a following situation. We have a gas, two sides of a box, and we have a hole in between, and we let the particles here fly around, and they may pass through the hole or not, and I have the possibility to close this. Now, you could look at a situation where all particles are only on the left half of the box and the hole is closed. And if you count the number of microstates which pay respect to that, this is, of course, by a factor 2 to the n smaller than all possible microstates you have to the full system. So in this case, if you say, okay, if you look at the volume, or if you paint in color all these microstates, which reflect this kind of macroscopic situation with the gas on one side, this is a very, very small volume. Much smaller compared to the volume where it's half-half. And in between there will be volumes where the ratio between the particles on the left and on the right, where you have some different densities, but it's not 0 and 1. You have something in between. Now, this is the idea. So this is just a picture. This is just simple combinatorics. I haven't discussed the evolution equations at all. The only thing which I have used is coming from the evolution equations that I look at the invariant measure, which is important, namely the Lebesgue measure of the system. Now, the idea of Boltzmann was now if you have some omega, which sits in this black area here, and it starts to evolve, that typically the behavior will be that eventually it will enter the place of larger volume. Well, the other way around, you don't encounter. If you start with some typical initial condition in the large box and you let it evolve, it will take a ridiculously long time to get you into this black area. And the time which Boltzmann gives, you can show for systems of many particles, is so large that you should not expect to see that during your lifetime. Now, this is the idea of the Boltzmann entropy, and I think it's remarkable, ingenious, and this will be important for our later discussion. So, irreversibility is, in this case, a result of the very special initial conditions. You start in the black area, you go to the larger volumes, but typically not backwards, or only after a very long time. Well, there's other options, and this is what I would like to discuss in the last part of my talk, suggested by Jean Carroll. I will come to that. This is some announcement of what is going to happen in the main part of this presentation. Well, the other option by Jean Carroll assumes that there's no normalizable invariant measure. As I said, I come to that in the main talk. Talking about Boltzmann entropy, I would also like to say a few words about Gibbs entropy. So Gibbs uses as entropy formula the Boltzmann constant and the integral of rho ln rho. And rho here should be understood as the probability density. And similar as in the citations before, where I told you, you should not expect that you get some kind of nonlinear equation if you're in a system of few particles. So you should not mess with probability density and empirical density. I think here Gibbs somehow falls into this kind of trap. And I would like to say why this Gibbs entropy is not the right idea to explain Clausius entropy in the macroscopic situations. But first of all, it is constant under Newtonian dynamics. And you know, each function on the phase space, if you evolve and take the integral, you will get something which is constant under Newtonian dynamics. Well, the whole meaning of entropy is change, right? So having something which is constant is not something which should be called entropy in any means. And of course, it will not reflect the Clausius entropy, which is in fact subject of change, which is empirically well understood. Well, only in the boring case of equilibrium states, it gives the right notion of an entropy, but in these cases, it's exactly the same as Boltzmann entropy, so it doesn't give us any different insights. And the Gibbs entropy is not a random variable in contrast to Boltzmann. And in the next slide, I would like to make this point that integrating out these, integrating over the probability space is not the thing you should do. Well, the example is very simple. It's the following. You ask your friend to turn on the fridge in case of good weather, right? But maybe you sit in a room where you have no windows, you don't know what the weather might be today. And given your ignorance about the weather, the probability that the fridge is on is given by some number. Let's say, for example, P equal to 1/2. Now, the fridge, of course, when you turn it on, changes the entropy in the gas. Well, it needs not be a fridge. It can be any heat engine, whatever you like, anything where the entropy is changed. And of course, if I now sit in the room and I'm unclear about the weather and say the weather is with probability 1/2 good, 1/2 bad, well, in the one case, the entropy will change to S on because the fridge was turned on. In the other case, it will change to S off because it was turned off. And if I want to define an entropy, which really gives the Clausius entropy, which resembles Clausius, the only reasonable explanation is that I say, okay, my S will be a random variable. With a certain probability, it will be S on. With another probability, it will be S off. And altogether, I think one sees that Gibbs fails in giving a microscopic explanation of Clausius. Well, there's a very nice paper, which I like very much. And I'm not saying that because the author is in the audience, which I recommend reading. It's the paper Science of Chaos or Chaos in Science, which I would recommend to anybody. I think it points in the right direction, and maybe in the discussion, Jean will have a minute if he wants to comment on that. Okay, this is somehow the setting, and I have now already given you the teasers of what's happening in the main talk. I would like to talk about the case one, show you how in the rather simple situation where the entropy stays constant, you can give rise to an effective description for an n-body system. And the other thing is, I would like to show you that if you drop the assumption that your invariant measure is normalizable, that you might get growth in entropy without the need of a past hypothesis. So this is what's going to happen next. Thank you.
So thank you, Peter, for this very nice introduction. And before we start the core talk, I would like to open it up for questions. So if you have any question on this more general part of the talk, you are now welcome to ask. Just raise your hand or show us somehow that you want to ask a question. So, Michael, you are having a question or just saying hello?
Oh, no, I just wanted to wave my hand. So
I see.
Peter gave a very nice presentation so far. No question, of course.
Thank you, Niki. Grüß dich.
Then we can
Thanks a
also
lot.
hop on to the core talk if you guys like.
Yeah, so if there are no questions, let's just go on to the core talk and then we can have questions afterwards. Okay, Peter, please.
Okay, thank you very much. So this is the main part of the talk, and it was not so easy to, when I was asked to give this lecture, I struggled a lot, and I thought about, well, there's so many things to be said, and on the one thing, finally I decided also in this time frame and everything which I have to focus on two different things, right? And the focus is that I would like to talk about rigorous derivations of effective equations and just give you an example where this can be done in a certain way. And in the second talk, since I think it's very interesting to have systems where the entropy changes, and I didn't want to since this is a very interesting question when it comes to micro to macro bridges, I didn't want to leave that out, and I allowed myself then to go to this second part in the main part of the talk where I talk about this. Now, in the first part, this is some kind of recent research result, which is where the most technical ideas were developed already a few years ago. In the first slide, I introduced my former students, and those former students were involved into this. Now, think of a plasma. Plasma is often called a fourth state of matter, and it's made of electrons and positively charged ions. And in a plasma situation, typically the ions are much heavier than the electrons. And very short time scales, there's a good arguments on a heuristic level that the electrons will shield the ions. So the ion-ion repulsion will be shielded by clouds of electrons around the ions. On a far distance, the ions look neutral. But if you get closer, you have still some interaction between the ions if they are close to each other. So it's effectively described by a cloud of interacting ions with short-range interaction. Well, the length scale of the interaction will depend on the electron density. This is not some kind of surprise. Well, physicists like to call this Debye length, the length scale of the interaction you get by this effect. So you could do what I did before, as I said, starting just from this many-body system and derive Vlasov, do this with rigor. Since I wanted to present something which is a little bit more recent, I wanted to tell you that this can be generalized to other situations. And here we start with something, which is also effective description from the very beginning. So some kind of, we could call it a mesoscopic system, where you have already used some kind of limiting argument to get something effective out, but still it involves many ions. In that sense, it's still microscopic. So the microscopic system is n interacting particles with Newtonian mechanics. We had this system before already. I just copied it here, and I would like to come to this slide, which is visible now. The force on the chase particle is some kind of interaction force, and my force now scales in the following way. I have a coupling n to the -1 plus 3 beta, and v n to the beta q. And the beta I will be able to use for technical reasons. I think what I will do holds also for other versions of betas, but for those beta, I can make a rigorous proof is smaller or equal to 1/7. I assume that V is compactly supported and has a bounded derivative. Now, look at the influence of this interaction. Well, the volume of the range of the interaction goes like n to the -3 beta. The coupling constant is n to the -1 plus 3 beta. So effectively, each interaction is of order n to the -1, which is the same as in the introductional part of the talk, right? So each effect of the interaction is of n-1, but everybody has n interaction partners, more or less. Or in this case, it's a little bit different. So each interaction is of order n-1 plus 3 beta, and everybody has n +1 minus 3 beta interaction partners because of this smaller volume in V. So you would expect an effect which is of the right order. So macroscopic, you get a law of motion for the particle density, which is in this case not the Vlasov equation, but the so-called Vlasov-Dirac-Benny equation, which is just using the respective mean field force for the system, so the expectation value of the respective force term. Okay. Well, I would like to announce some mathematical results in this direction. Well, the derivation of such effective equations goes back to the 70s. There's papers by Neunzert and Wick from 74, Braun and Hepp. There's also later, they want many people to mention. I mentioned François here, but the list could be much, much longer than this. And the physically interesting case will be the plasma or the galaxy, which I discussed before, or this kind of, at least if you start with a system in between. So you have either Coulomb when describing the plasma, or the effective model I gave you now for the galaxy would assume that you have attractive Coulomb, which is this kind of force. So this is not a global Lipschitz force anymore. And also the force we are talking about is not globally Lipschitz. Well, Sarfati and Dürrings could prove the validity of some effective equations, but only in a monokinetic situation. This is the limitation of what they do, but still, I think it's a very nice and remarkable paper because they really can treat the Coulomb case, well, only the repulsive situation. Now, in the last, let's say, 10 years, roughly, there has been other people working on that. Oreilles and Jabin are to mention, with other co-workers, which looked at all kinds of different systems, and also some results I have with my students. And the idea is to look at Coulomb equations with cutoff. This is what we did in the past. And there was a paper which I learned about in a conference by Griffin Pickering and Jacobelli from 2018. And what Megan and Michaela did is they looked at this Vlasov-Dirac-Benny equations of the system I'm explaining now. And we had the impression that with our techniques, it might be possible to get a result which has maybe a better scaling of these interactions, so to improve this better compared to what was there in the literature. Now, what we will do, we will have to compare the microscopic description of the system with this density. And what we want to do here is we bring this rho 2 on the level of trajectories in a sense. So we want to compare two different trajectories, and the one trajectory will be given by the effective equation. So the so-called Vlasov-Dirac-Benny equation, it's the kind of equation we had before, but the interaction force term is now the average coming from this special scaling of the potential. Now I define a new evolution equation, which is again Newtonian. So the Q bar dot will be given by P bar. But now the force term of the particles, the VF bar, so this is the force term acting on the jth particle, is given by this kind of convolution of our density with the one particle force. I assume that initially our particle positions match, and I want to prove that also at time t, the position and velocities of our particle will not differ significantly from each other. In which sense, I mean that this approximation hold, this will be defined in a second. Now, what we do is we look at a probabilistic situation. So again, we assume, as I explained already in the introduction, that our initial positions and velocities of the stars will be IID, or in this case of the ions in the plasma will be IID. So we have a sample space. The sample space is R6n, and the probability measure on the sample space is given by the product measure of these rho 0, which I have assumed to hold at the beginning. So I have a rho 0. With this rho 0, I put my ions into the plasma in an IID way, and this defines an initial empirical density and initial sample, and now I let things evolve. Now, with this description, the Q's, P's, Q bar, and P bars, these are all objects which can be derived from the initial sample, so they are random variables. And of course, since the bar force here does not lead to interaction or correlations between the particles, it acts like an external field on the particles, the independence will be conserved as time evolves. Independence is important, well, that it's identically distributed, not so much, that for the law of large numbers, independence is important. You could have different distributions as you like, but it's IID also at time t. So the probability density for the bar situation will be exactly given by this product measure where rho solves this kind of Vlasov-Dirac-Benny equation, which I've written down before. Now, a law of large numbers then tells you, well, in fact, the textbook version of law of large numbers tells you that the empirical density of Q bar P bar converges in a weak sense towards the rho T Q P. So this is very German, right, to say converge against. So this is kind of, sorry for that, too. I'm German, so here you can see it. So this is a kind of the convergence which you have. And the goal is to show that also after some time t, the Q and the P system with the Q bar and P bar system match. This is what we want to do. Well, as I said, if you have weak notion of convergence, then here it's in fact really textbook law of large numbers which you can use. Now the theorem, I would like to formulate a theorem which we can prove, and therefore I would like to introduce some kind of time-dependent random variable which looks in the following way. So I take the position and the velocity of the true guy, and the position I multiply with square root of ln. Why is something I would like to explain later. And I take the position and the velocity of the mean field trajectory of this auxiliary time evolution, and I compare those two. And this is the maximum norm on my R6n space. So in other words, I look at the largest difference I see in any particle, and I take the largest difference which I find, and I have this kind of set, and this is the set of bad situations, and a situation is bad if one of these particles has a deviation which is more than n to the minus beta. Beta was my length scale of the system, right, of the interaction. It's the length scale which I have in the system coming from the interaction. So if two particles deviate from each other more than n to the minus beta, well, I say it's a bad situation, and I have some assumption on the initial density. So if I integrate the density against the with the velocity, then it should stay bounded. Now I write a theorem, and the theorem says that for any time t and for any gamma larger than 0, I can find a constant c gamma such that the probability to be in such a bad situation is bounded by c gamma n to the minus gamma. So that means that very rarely you only see that particles deviate from another particle more than the length scales in the system coming from the interaction. You see, this is a very high standard. So I have very high standards in calling particles good or bad. If only one single particle deviates more than n to the minus beta, this is already a hit for the set A. And I say that the probability of A is bounded, this is smaller or equal than any polynomial. Well, in fact, with a little bit more effort, we could get some exponential, something which is some exponential bound here, but I'm not going into that. Okay. For this talk, I want to show you that the bound is, in fact, c times e to the c square root ln nt times n to the minus beta. This is what I can do here, which simplifies the notation a little bit for the next slides. So I will not do the full-fledged proof where I can get any c gamma n to the minus gamma. So this is a little bit milder. So my gamma here for the rest of the talk, I just choose beta, right? I think this is already good to see that the probability gets small. Why does this get small? Well, if my time t is order 1, you know that e to the square root of ln n times a constant is smaller than any negative exponent of n. So this here we go to 0 for any fixed t as n goes to infinity. This is easy to see, right? E to the c times ln n would be n to the c. But if I multiply that with 1 over square root of ln n, which I did here, I get something which is much smaller than that. So you see that this here will, of course, be dominant compared to that guy here. Now, what I define is now the following random variable. I call it JT. So this has something to do with the set AT I defined above. So this J is now a random variable. And for the random variable has the following definition. So I take the minimum of the number 1 and this kind of distance. So whenever this distance here is larger than n to the minus beta, I take the 1. Whenever it's smaller than n to the minus beta, I just take n to the beta times this distance. So this is what I do. It is easy to see that the value of this jt is exactly 1 if omega is in AT. This is easy to see because if omega is in AT, that means that this distance here is larger equal to n minus beta than this here is larger equal to 1, and the other way around. Now, what I'm going to prove, or what I'm going to show you, that is that J fulfills some kind of Grönwall estimate. So the time derivative of the expectation value of J is bounded by C times the square root ln n of times the expectation value of J times something small for some delta larger than 0. And this Grönwall's lemma then implies the boundedness as it was announced. A side remark, since the probability of AT since JT is positive, the probability of AT is always bounded by the expectation value of JT. Why that? Well, the expectation value of JT is, of course, the probability that JT is 1 times the probability that JT is 1 plus all the other values that JT can have times the probability that JT has this value. Well, this is the naive formula for the expectation value. And of course, taking already 1 times the probability that JT is 1, you get the probability of A, and this already gives a bound of this expectation value. So once I've proven this lemma over here and use Grönwall, I get a control of P. So expectation value of J controls P of A, so controlling the expectation value of J, I'm done. Now, just a side remark, the expectation value of our J is easier to control than this directly. Well, the probability of A is the same as the expectation value of the characteristic function of A. And the J is something like a smeared out characteristic function of A. I would like to say a few words on how this is done. Let me skip that, but let's come to the proof. Now, if you now go and want to show that this Grönwall estimate holds, you derive the expectation value here of J with respect to T, and you get two things. You get, first of all, a contribution which comes from the change in the positions. So the change in the positions here of the particles will be proportional to the change in the momenta. And since I've given different weight to the positions in momenta, I get a square root of ln n here, which is not a problem because this is still in agreement with our Grönwall estimate I was looking for. 1 square root of ln n I can afford because a square root of ln n in the exponent is still something I can handle with my estimates. So this is what here, this is still fine. Now, let's look at the time derivative of the positions. Well, the time derivative of the positions is, of course, then given by n to the beta times the forces acting on the particle, respectively the mean forces acting on the mean field particles. And this thing I can write down in another way. Well, the goal is to use law of large numbers. So I have the force on the particles. Here it's not IID, so it's red because it's not in the good situation where I can use law of large numbers. But F bar, Q bar, this is good. But I use triangle inequality and I write F of Q minus F of bar of Q bar in the following way. I just added F of Q bar and subtracted it again and used triangle inequality to arrive at this kind of equation. Now with my boundary condition I have, and this is something I did, sorry, I have to say that here. Now, if the JT has reached the maximal value, then this distance here is bounded by n to the minus beta. So for the time derivative of my J, there is some trivial situation. As soon as J has reached the value 1, it cannot grow any further because I have cut it off at 1, right? So in cases where this value is 1, which means that the distance is larger than n to the minus beta, then the time derivative of J is trivial. It's 0 or negative. So only in the other cases where this distance is smaller than n to the minus beta, I need to do the estimates. This I call boundary conditions. Only in the cases where the distance I've written here is smaller than n to the minus beta, the change in j is non-trivial and I have to estimate something. But now comes the following. Since this n to the minus beta is the length scales in my system and the length scales in the interaction, I can show easily that I can replace this distance here using the mean value theorem of calculus. So the distance of f at q minus f at q bar is by the mean value theorem given by the for the derivative of f. I call the derivative of f, I call g, at some position in between. And since the length scales in my interaction and the length scale of the distance between q and q bar, everybody lives on the same length scales. So my derivative on the intermediate position is of the same order as the derivative on this position q bar. So this here can be replaced by c times g of q bar. So this involves two things. First, this equivalence of length scales and the mean value theorem. And now everything is green and I do law of large numbers and the rest then follows. Using law of large numbers, you see that this here is small. This here is something bounded times q minus q bar. In fact, if you now do the integration here, you get some ln. This ln will help you to overcome that because ln n times q minus q bar can be written as, and I write that, so here the bound is square root ln n times square root ln n. If you do all the details, q minus q bar. And this here was one part of the j, right? So I get again square root of ln n times j, which is in line with the Grünwald estimate I was aiming for. Okay. So this is one example how you can derive effective equations for a many-body system and arrive at this kind of situation where you have some non-trivial evolution equation. And the other thing I wanted to do is to talk about this error of time without past hypothesis. Well, this is a very different topic, as I said, than the one. So the first case is now the entropy constant thing. Now, the second question I think I wanted to address here is the following, and this will be explained by a picture. Remember in the pre-announcement, I had this explanation of the growth of the Boltzmann entropy. I said I start at a certain point in a corner and then I evolve. Now the idea is that you try to get the growth in entropy, you have to assume that you start in a very, very special position here in your box. And I want to explain that it might be possible to drop this condition, assume that there is no box. So the probability or the measure is unbounded. It's not normalizable. Then you cannot draw this box around it. And you could say, well, if there is some unboundedness on the system, and no matter where you start, there might be larger and larger volumes. And now you start somewhere, and typically you would go into this larger area rather than the smaller one. This could also explain for the growth in the entropy. This is an idea which goes back to Jean Carroll, as I have announced. And our goal is to find now a microscopic system which really resembles this idea. And I would like to give you a microscopic system where we are rather convinced that it shows this behavior, although the rigorous proof is not complete yet. So I consider n particles on a 3D torus with total energy 0. And I have no normalized invariant measure if I assume that I have attractive Coulomb interaction between the particles. Well, because the kinetic energy will be unbounded on omega. Now, ET is the sum of the particles, where ETJ is the kinetic energy particle J at time t. So this is what I call ET. So this ET will be unbounded. Well, if n is 2, one could in fact show that you can show that there is all these features which I explained now, that there is a normalizable measure for n equal to 2, it's constant, and I assume, of course, that n is very large. And the conjecture, it's something we want to prove. It's not done. The proof yet is that for any c larger than 0, and for sufficiently large n, there is a time such that the energy overcomes this constant c. So that's the kinetic energy of the system will stay unbounded. Well, of course, I need to assume that I have typical initial states, not something where everything just rotates in circles in a sense, right? This is like always the assumption we have to make. Next step, we want to show that the Boltzmann entropy in fact grows. While this kinetic energy, it's not obvious that this gives then the right picture also for the Boltzmann entropy, that this is ever growing. Now, what do we do here? How do we have a chance to prove that? And I think it's kind of remarkable. We want to use ergodicity of the system. We want to use some ergodicity argument to show our conjecture. And this might be now confusing because I just said there is no normalizable measure. To use ergodicity is, of course, based on the fact that there is a normalizable measure. And I would like to present you the idea how this can still be done. And the argument is that we make an argument by contradiction. We assume by contradiction that E stays bounded. So we assume for contradiction against this conjecture that there is a C, that the total energy will be bounded by this C. Now, we could say, well, if the total energy is bounded, we could introduce a cutoff for the potential. We cut the potential off in such a way that the negative potential is never reached, right? So if the total kinetic energy is bounded by C, the total potential energy is bounded by minus C from below. And that means the potential can never be smaller than minus C. So if you make a cutoff, for example, at minus 3C, we're safe, right? We have a new system, Newtonian system now with cutoff in the interaction. But under this assumption, which I have made, both systems match for all times. Now, for this new system, I can use ergodicity. That's the thing. Now, the central challenge is really to give a mathematical rigorous proof for such a system with cutoff. You know that this is already hard and challenging, and this is what we are working on. Now, if we have proven ergodicity, we use the ergodic theorem as it's written here, which means that almost surely we will overcome this kind of, if the cutoff was minus 3C, we will reach a situation eventually where the total potential energy in the system will be minus CC, because that is an allowed area also for this auxiliary system with cutoff. So we will reach it using ergodicity. And this here then is a contradiction to the fact that our kinetic energy is bounded by C, which means our potential energy cannot be smaller than minus C. And we get a contradiction. Now, what we are aiming for at the moment is, I think, proving this kind of behavior, that you have a growth in entropy without a past hypothesis. It's already nice to have a model which needs not be so extremely physical, right? To have just a dynamical system where you can make this point. In general, it's possible to get this growth in entropy in dynamic systems without past hypothesis. That's worth a lot already. So what we're doing at the moment is we try to model or change the model a little bit, such that it might be less physical, but it's easier to prove some ergodicity for this system with cutoff and to make this contradictory argument and show that the kinetic energy is ever growing. And in another step, the idea is then to show that also the Boltzmann entropy grows all the time. Now, as I said, it might be that the energy fluctuations are only short-lived, and we want to argue that really the entropy is growing. This is the final thing, the proof of growth in the entropy for such a system. However, we would expect that this potential energy, if you have 3 particle collisions, will be transferred to other particles, and eventually, if you wait sufficiently long and the kinetic energy is unbounded, that some of these energy will be given away to single particles so that the system in fact heats up. This is what I would expect, but as I said, I don't have a proof. Now, these were the 2 points I wanted to make. There is derivation of effective equations for microscopic systems in the very simple situation where there is no growth in entropy, where you get this kind of mean limit behavior. I showed you the techniques how this can be done. I showed you that you could try to reach out to systems which are more interesting and try to prove their effective behavior, a formula for the energy, also in other situations where it's more interesting, where you really have an error of time. And with this, I would like to thank you for the attention. Thanks a lot.
Thank you, Peter, very much. So I think this was a very interesting talk, at least for me, and I hope for others too, yes. So let's open it up for discussion and questions. So whoever has a question, please raise your hand and then I can call you and you may ask. So people are still...
Maybe a quick question.
Okay, Michael, go ahead.
Peter, when you, in the last part here of your talk, when you were pointing out you want to use ergodicity, in which sense could one argue with timescale arguments, like with a Poincaré recurrence theorem, of course. So that's true, it happens, but it happens on such long timescale that it will be irrelevant. So could one be skeptical whether your proof that you are aiming at would be maybe suffering from the same criticism, that it's not relevant for practical purposes?
Well, that's a very good point, Michael. And this is something one has to discuss, that it might be one could have the impression that it's unpractical, but we are in the very special situation that we do not have a normalizable measure, right? So we start somewhere in our space, right? And I don't know how to explain that. So we start at some initial conditions, and the energy will be unbounded. And you say, okay, the question is, how long will it take to overcome a certain bound? But eventually all bounds will be overcome at a certain amount of time. So I think since this t here will be infinity, right? The constant can be arbitrarily large. We don't have really a scale in that sense, right? Since this is unscaled, I would not expect that you get a t scale. How can I explain that? I don't know. So the long time behavior will be that eventually it heats up to arbitrary high temperatures. So you don't have a temperature scale which is fixed, which is given. So there is no parameter for the time scale in that sense. Does that make sense, what I'm saying? I'm not sure.
No, I think I'm getting the hang of it. But another comment in that same direction is in the context of stellar dynamics. Of course, you have then, instead of attractive Coulomb, you have only gravitating system. There's an old paper by Heggie, long paper actually, maybe from the 80s or so, something like that. And so he's estimating when you take just Newtonian gravitational interaction and point particles, that you get this heating effect. So that means in free space you are shrinking. In physical space, but in velocity space you're expanding. No.
Okay. Yes.
The heating, and so he has estimates, but of course it's not a rigorous paper.
Exactly. No, I think that goes into this direction.
So you could maybe take a look at that, whether there's any useful idea that one can make rigorous in there. No? So it's.
I think it's useful, and I didn't mention Antonov. He has a paper from the 50s where he already has ideas in this direction, which also that result is not rigorous. So I think the idea which is there, that you have unboundedness of the kinetic energy when particles get closed, and in principle you could heat up arbitrarily strong. This is there already. Now the question is does this conjecture hold? So is it really happening for typical initial states that the potential energy will eventually be arbitrarily large? The next question will be, is this only peaks because of two particles come close and escape from each other already? Do you just have very high peaks and everything is as cool, or does really the system heat up in a sense? then the next question would be, does that really mean the entropy, the Boltzmann entropy grows? I think the answer will then be yes. And then what you said before is also then relevant. Is this happening in a way, let's say, on timescales that this explains what we see in nature, right? These are all open questions. I agree. We're just entering the business, and I think it's a very interesting and important topic where there should be more research should be done, and we are just at the beginning. So.
Okay. Is there any question? So otherwise, I would also ask a question. So in case, in this case, for the heating up of the system, so just what we were talking about before, you take the kinetic energy then to be a macro variable of the system, which basically enters the entropy formula. So
well,
you learned that basically.
You know that this is problematic, right?
Okay, but this would mean well, otherwise, how would this increase in kinetic energy? Well,
yeah, that's a good point, Paula. Again, now this conjecture is a first step. Now, the first step is to prove that there is an increase in the kinetic energy. If you don't have that, you couldn't forgot the system from the very beginning.
Sure, I mean, I agree.
The second step is then to see if really the Boltzmann entropy growth. And as you have proven in your master thesis, one has to be careful with the macro variables, right? For those who are not familiar with Paula's thesis, what she did is she looked at a system in R3, which just is subject to an ideal gas in a 3, an ideal gas cloud, which just evolves freely, and then look at the entropy. And if as a macro variable, you take the density in space, it seems that the entropy will change. But you at the same time see that if you also take the velocities or the variance in the velocities, the system cools down and the entropy stays constant. So just picking one of the macro variables is dangerous. It might seem that the entropy changes while it does not. And here, of course, you could run into the same problem in principle. So I think the fact that the entropy, the energy changes, first of all, the changes in the energy will be some kind of peaks, right? So let's look at the following situation. You have two particles, they approach each other and get extremely close. So all the other particles are extremely far away on that scale here. So they don't matter so much and they escape from each other when they get extremely close. So the very strong peaks in the energy will just be peaks, right? And the particle will go back. And I would say this does not change the entropy of the system because you're back to the old state, obviously, right? But what also will happen is that even in more rare situations, the third particle might get close and some of the kinetic energy will not be given back to the rest of the collision, but will be consumed by this third particle which flies around, which forces the two guys here to keep some negative potential energy, so to stay close to each other. So eventually I would expect that you have particles shooting around in some kind of, double, let's call them double stars or however you want to call them, that give some, their potential energy is the source for the heating, right? This is what happens. And this should increase the entropy. This is what I expect. This is what my intuition tells. But to make a rigorous proof, we're still away from that. So the first step is the conjecture, then to find some more effects which really, there is hope that they can explain a change in entropy and then really to see a change in the entropy for the system.
Yeah, that seems reasonable. I agree on that. So there's another hand by...
Hi, Yves. Nice to see you.
Hi, Michael. Hi, Peter. Glad to see you indeed. I have a question about the scaling of your effect now with n. If you need a third particle to come along, and you let your interaction rescale with n, and also let n go to infinity, can we hope the entropy to increase, or will it or are we going to end up with effective equations in a second order in 1 over n or whatever like that?
Very, very good point, Yves. And the point is now, if you would take, and this is related to what Michael was saying before, if you would take a fixed time interval or a certain time interval, even something which grows mildly in n, because of your argument, one expect that the effect of the three-particle collision vanishes in the n to the infinity limit, right? Because we have the coupling which we have, and the events are extremely rare, right? But I think that if you wait even longer, eventually you will have a growth in the entropy. And now comes the question, what is the time scale, right? Is it ridiculously large, such that you say, okay, in an experiment, you wouldn't see that? Or is it that you see a growth in the entropy? And if I think my feeling in the stomach tells me I would expect you see the growth on a very long time scale, which is not ridiculously long, more polynomial than exponential. But I might be wrong. And this is just an item of interesting research which we are doing now. And I think there is the hope in the community of people who follow these ideas of Jean Carroll that some systems like that can be found. May it be this model or another one. So we're looking for this. And the question, I think the question is, and that's why I put here the word conjecture, is this really explaining the growth in entropy starting from a microscopic system without other problems one has? Yes or no? And I'm not 100% sure. If I would have to bet, I would say I think yes, but I agree. And I think what you're saying is completely right. It will be rare, and the question is, will it be so rare that you have something which in the n to infinity limit takes an exponential time, and we can forget about that, right?
Thanks.
Okay. Thank you. So there's another question by Dirk.
Yeah, hi Peter. Thank you very much for this nice talk. Another question, like putting it around, I mean, the particle system on the right bottom that you drew, this double star or how you want to call it, this bound state. If this is the engine, as I understood about this, for this energy increase, does it mean, or could you, for example, show something like that for interactions that are very smooth, for example, at small distances or even zero, that you could maybe prove a negative result, that you don't find this energy?
Absolutely. No, this is then, I think if you have something nice and smooth, then I would expect, although I cannot prove it, that the ergodic theorem holds from the very beginning, because from the very beginning you have a system which is normalizable. So let me draw the picture. I have some space here for picture on my last thank you slide. Now, if you would have some kind of draw the picture, here's the positions and here's the velocities, and you have two particles coming very close, and you draw the curve of constant energy. So what I'm drawing here is the curve of constant energy. So here's, for example, x1 minus x2 is small. Here's let's say x1 minus x3 is small. You know, I don't know if I'm not good at drawing things, but I hope you understand what I mean. Because you have some source of potential energy, and if you draw that, let's say, and you're on a torus, let's say, and you cut off somewhere, if you would make a cutoff here, the volume would be bounded, right? And then you have a normalizable measure. It's a probability measure, and you have the old stuff, ergodic, if it's ergodic theorem, and for sure Poincaré recurrence. Now the goal is to say, okay, if we do the Coulomb, that these volumes you get here are infinite. We cannot normalize the measure anymore, and then the hope is that we can prove something. And with the conjecture, I'm quite sure, if ergodicity is true, which I'm quite sure, although I don't have a rigorous proof, I'm sure that ergodicity holds. So with the conjecture as it's written, I'm sure that it holds. I just don't have a proof. But the other steps, which I said, and which, of course, for very good reasons, Michael and Yves addressed, I'm not so sure anymore, but we do research in this direction, and we hope that, in fact, we say yes. And if we don't say yes for this system, we're looking for some system where this can be done in a way. And if we see that it fails completely, and we have a good argument that this fails completely, that's as interesting to have an example where it works, I think. Because then this would mean this argument is off the table, and then we have to go back to Boltzmann and past hypothesis, right? And then that's the only explanation that remains, in a sense, for the growth in entropy, and I don't have any other one.
I see. Thank you.
Okay. May I also? I have another question. So, but if you look at just the Newtonian n-body system, so just n particles attracting each other according to the Newtonian gravitational law, then you have these results also by Sari and Marshall and Sari on the long time behavior, where you see that particles cluster into galaxies or into binary, into some pairs of stars and so on, and you have these long time results that this clustering happens, and this should also somehow add to this increase in kinetic energy.
Yeah, that speaks for us, in a sense of what I was saying here. No, that's true. That's a good argument in this direction. It's not the final argument, right?
Exactly, but it's at least in the same direction, I think.
Absolutely, yeah. This goes into this direction. Yes.
Okay, is there any other question to Peter? So if not, I would like to thank you again for coming. I'm very happy that you have been our first speaker of this winter term. And
thanks a lot, Paula.
Yeah, happy to see you again. All of you. Dirk, you want to say something in the end, or?
I don't have much more to say, except for that the routine will be that Fabian will invite us for the next sessions. So we don't have a very regular schedule, but we have rather fewer talks, but then in this new format, so that also we have a broad audience that can listen to it. Yeah, I was very happy, Peter, to have you here.
Thanks a lot.
And that we got the series going again. I look forward to seeing all of you in the next events.
Okay. Bye now.
Thank you very much. Bye-bye to all of you.
Bye-bye.
Thanks for the great talk.
Thank you all. Thank you, Peter.
Welcome. Bye.
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 Thank you.